Well, we're going to talk about microphones, not about the way they transduce energy from acoustic to electrical, but some characteristics that we need to think about them. One is the polar response. So, what is the pickup pattern for the microphone like? And then the other one is the frequency response. How well does the microphone reproduce sounds at different frequencies across the audible spectrum? So that's the focus of this particular video. Let's go ahead and turn to the PowerPoint. There you see the basic topics, polar response diagrams, and frequency response curves. So let's start off with directional characteristics. I'm fairly certain that you're familiar with some of these. Most importantly, you're familiar with this first one here. This is the cardioid pattern. Looks kind of like a kidney. Sometimes people think of it looking like a heart. That's how we get the name cardioid. We also are probably familiar with this bidirectional microphone image and the omnidirectional microphone response curve. And then this one, which kind of looks like Squidward there, this is going to be a higher level of directional microphone that is extending the reach and making it narrower than the cardioid, but we have a problem with it because when we try to narrow the pickup pattern in the front of the microphone, we end up picking up more sound behind, whereas the cardioid is really good at blocking the sound from behind. The Omni, of course, is really good for picking up all across, all around us. And so let's go ahead and look at some of these things, which I'm pretty sure is a good review for you. So omnidirectional picks up all around. Bidirectional picks up in front and back, two opposite sounds. Unidirectional picks up right in front. Now keep in mind, unidirectional is a general name for microphones that pick up in one direction, but we do have a family of those microphones that are more specifically labeled so we understand how they're picking up. So let's take a look at the family of cardioid mics. We've got quite a range available to us. We've got a traditional cardioid, we've got a supercardioid, a hypercardioid. Beyond that, we've got an ultracardioid. And as you take a look at this pattern that's being displayed here, you can notice that from behind, 180 degrees behind the microphone and the cardioid is being pretty much cut off. But when we get to that supercardioid, we're getting a little bit of pickup there. When we get to the hypercardioid, we're getting even more. So as I said, as we narrow that pickup pattern, we have to be very conscious of what's happening behind the mic because we're picking up more of that sound behind the mic. And this is the image here that sort of gives you the idea of what's going on with these patterns. So the front of the mic is here, and we're interested in picking up in that direction. If it's an omnidirectional, it's going to pick up all around. But if it's a cardioid, it's going to pick up only in front and around the sides, but narrowly around the sides, and more narrowly as we increase the cardioid pattern to make it narrower and narrower. Here's another way of looking at it, which I like overall. This is something where it highlights the idea of the angle of acceptance. So I always like to have people try to envision what it would be like to place a microphone and try to pick up sound that's coming from the front. When it's an omni, it's really easy to understand. When it's a cardioid, it's still somewhat easy to understand. But when we start getting narrower through supercardioid, hypercardioid, ultracardioid, we actually have to start to think about, well, what is the width of that pickup? What is the angle in front of us that we can sort of visualize as being the pickup area for the microphone? And so that's why I like to highlight this acceptance angle degrees here. And I'm not asking you to memorize these. That wouldn't make any sense. You don't have to memorize them, but having some sense of it will make a difference. So understanding that a cardioid is going to be about 130 degrees, right? So if it's 180 degrees here, 130 degrees is taking off just about 25 degrees off each side, right? If we're going to 115 degrees, you divide that in half, right? And you think about the angle here. And as we think about that, and we're standing and looking in front of us at the place that we're going to try to microphone or capture with a microphone, we can think about those angles even by extending our arms and moving them to 180 degrees and narrower. That will give us some sense of where that microphone is going to be able to pick up most effectively. And hypercardioid at 105, bidirectional is directly in front, directly in back. So having some sense of these is helpful when you're thinking about placing mics and working with mics that have different pickup patterns. So let's look at the sound of the microphones as reflected in graphs. This is an example of a frequency response curve. What it shows us across the bottom is the audible spectrum, 20 hertz to 20,000 hertz. And each of these lines represents, in this case, 5 dBs of volume. So what happens is they put sound in at a certain level of dB, and then they measure the sound coming out, and they do it at every one of these frequencies across the spectrum. And then they plot it for us so that we can see, well, what's happening with the microphone. When we take a look at this microphone, we can see, looking far to the left here, that there's a drop-off, right? So if we're putting in this much sound at these frequencies, at 200, we're getting out what we put in. At 100, we're getting out a little less than what we put in. And as we go a little bit lower to maybe 60 here, we're actually getting 5 dB of low frequency less than what we were putting in. We're getting 10 degrees, or 10 dBs I should say, of sound less at 40 hertz than we were putting in. So this microphone is not as responsive in those low frequencies as perhaps we might want. But of course we have to compare it to other mics. But it's doing okay picking up anywhere from 100 and on. It's doing pretty well. So here we've got it moving across, and it's getting out pretty much what it's putting in. We've got 200, 300, 400, 500, all the way up to 1 kilohertz, up to 2 kilohertz. We're getting out exactly what we put in for the most part. But as we start getting above 2 kilohertz to 3, 4, and 5, and 6, 7, 8, 9, even 10, we're actually getting a boost. So here's where we can reflect back on those tonal categories, right? We think about, well, what is the category here of sound where we're getting a boost, right? So 5 kilohertz to 20 kilohertz, that's really going to be our treble area. So for a good portion of that treble area, we're getting a boost. But at around 10K, we're starting to lose that energy. We're getting less out than we put in. So we're not performing as well. So the microphone frequency response curve shows us the response that the microphone has in terms of level across the audible spectrum. Let's take a look at another one. So here's one that's kind of interesting because it's got 3 different lines on it. One at 0 degrees, one at 180 degrees, and one at 150 plus or minus 10. So what we get with this particular image is an idea that they're showing us the response, but not directly in front of the mic by itself. 0 degrees is directly in front of the mic. 180 degrees is directly behind the mic. And then 150 plus or minus 10 is in an angle, not directly behind the mic, but off angle behind the mic. So we can see here that our highest level is going to be directly in front. Then at directly behind, it's at another level. And then off an angle behind, it's a little bit lower. So having these 3 lines in this way, where the 180 degrees is the second one in terms of the amount of level that's coming in or volume that's coming in, we can learn that this is some kind of cardioid pattern that is narrower than a traditional cardioid. Could be a supercardioid or a hypercardioid, because we are getting more sound directly behind than we are in the angles behind us. So this graph is showing us that. It is also showing us that it's at about 180 we're losing low frequency. And there's a little bit of boost here at about 6, 7, 8, 9K. So, 6, 7, 8, 9 is where it's getting a tiny bit of a boost. And again, this is 5 dB difference. So this is probably about 2.5 dB or 2 dB boost here at the higher frequencies. And you'll see that quite frequently actually with microphones, because there are a lot of people who like to have that little emphasis on the higher frequency. It makes it a little bit brighter, a little bit sharper, and there are a lot of people who like that kind of clarity, the sharpness in the microphone sound. Let's see, I think I have one more on here. I do indeed. So here's one that is showing us all the way down to 10 hertz, which is really unusual, and I'm guessing they probably didn't exactly measure it, but maybe they did. But it's showing that we've got a big drop off here, but that's 20, that's 30, and that's 40. So at 40 hertz, this microphone is showing us that we're getting the same amount of energy, same loudness of the sound out at 40 hertz that we put in. So in terms of comparisons, this microphone is doing much better in those low frequencies than the other two microphones whose patterns we were looking at. This one moves along, but then there's a little bit of a drop off here. So if that's 1,000 hertz, 2,000, 3,000, so 2,000, 3,000, 4,000, 5,000, we're actually losing some of those frequencies. And that is still in our mid-range area, right? Mid-range and upper mid-range. So that's something we have to be paying attention to. This is going to affect vocal sounds. But then we've got some peaks here at the 15K, and so we're seeing that there's a drop-off here that's severe. And so in this case, we're seeing that there's a bit of a boost at the high end to give that sharpness, but we are losing some of this level in that mid-range, upper mid-range area. So that's could be problematic and means it may not be great for voices, but may be really good for lower frequency instruments, let's say like an acoustic bass or something. So that's one of the ways that we think about these frequency response curves. So you can always look at a microphone specs and see what the polar response is. And keep in mind that polar responses can actually change across the frequency. And you can also see the frequency response. And this way you can get a sense for what are the most appropriate sources to record with these different microphones. What are the characteristics of the source from the standpoint of the frequencies that make it really good or really bad for certain kinds of microphones. So there we have our polar response and our frequency response, those characteristics of microphones described.